Okay. So, when we communicate, the transport layer goes down through the stack to the physical layer, and all the network devices, including routers, right, have to go back up the stack to the network layer and then back down, right? And so we might have other devices like LAN devices that only go through physical and data link in between here, but routers go to, but now we can ignore all of this entirely. And the transport layer virtually talks to the other transport layer without anything in between. And so the transport layer encapsulates the network packet. And the network packet contains what kind of addressing? And what we've mostly been talking about is IP, right? Network is mostly IP. And we've been talking about that. So, of course, one computer can talk to another computer on many different applications. So when we talk about transport layer, how does it distinguish what communication is going on?
Using the ports.
Ports, yes. We communicate with ports. Now, we'll see when we talk about the transport layer, it also contains the IP address, subheader and checksum and stuff, because there needs to be a little bit of glue. And in reality, when you create a socket, you tell it the IP and the port, even though that you're talking to the transport layer. There needs to be some kind of binding of that information. So, but really is what we're talking about is ports, right? So that one computer can talk to another computer in many different communications because they're computers and they can do that. And we can have a communication go on. So, recall from when we started out the class, we went over sockets. And when we went over sockets, we kind of described what was a TCP string. So the transport layer can do a TCP string like we talked about at the beginning of class. Don't worry if you don't remember, because we're going to talk about it extensively. But it also can talk about, over datagrams, right? So something that's less than a TCP string. So a TCP string is connection oriented. So we do a handshake and we establish connection, we establish sequence numbers and acknowledgments for those sequence numbers. But then we also have a datagram, which is UDP, and UDP just fires packets. So what are some of the characteristics of characteristics and differentiators of TCP versus UDP?
So you said connection oriented versus connectionless?
Yep. What else?
Stream. This is
Stream.
Sends data in stream.
Yeah, this is a stream.
And UDP is datagram.
A datagram, right?
Mm-hmm.
What else?
Cost.
Huh?
Cost.
Cost.
TCPS, like flow control and stuff like that.
Yeah. This part of connect, not, we'll call this no flow.
Reliability.
Reliability. Okay.
Amount of overhead.
Oh yeah.
With UDP, you don't have to confirm if you got received or not?
No?
No, I was just asking if that was one of the strings.
So, normally in UDP, you can confirm, but there's no So, and we'll talk about special cases for UDP, because UDP can have all of these things, right? But the application needs to take care of it. The transport layer does not take care of it. So when we talk about the transport layer in TCP versus UDP, this means that the transport layer itself takes care of all these things. So you can build a UDP and have the application do all of these things.
And what would be the downside of that?
Well, the downside of it is that TCP takes care of all of it, so it is very well coded and very streamlined, and often accelerated. UDP, if you were handling the application, it means that you're doing it yourself, which means it's likely to be buggier, it's not streamlined, and you're doing it in user space versus OS space. So the other one is length of content. Why is length of content restricted in UDP?
How much can you shove in a single packet?
It's because how much can you shove in a single packet? Now your application can reassemble multiple packets, right, on the other end. And just like we said, we can take care of all this stuff in UDP. We could do flow control, we could even do acknowledgements, all this other stuff. But then it would be your application layer that's taking care of that. So, and there are some applications that do that, because TCP is basically everything, right? Which means it has a very high overhead. It's everything in the kitchen sink. And UDP is nothing. UDP is basically the network stack with a tiny little header stuck on top of it. And so you're basically, whatever the network has is what UDP has. So, let's go back to that socket API. So instead of a client server, we're going to say an active computer and a passive computer. So the active computer is the one that initiates some kind of a communication, and the passive is the one that's sitting there waiting. It's very much like the client server model, right? So the what do we need to do from, let's start on the passive. Let's start on the passive side. What do we need to do to make this thing work?
Create a socket and listen.
So we need to create a socket, right?
Mm-hmm.
What else?
Listen.
There's something else that we need in there.
Bind.
We get a bind. What does bind do?
Assigns a port number to the socket.
Do you add
Yeah, it binds the port number to the socket. We have to do that because there has to be some way for the active one to initiate a communication to the server. So the server binds the port because it knows what services that it's offering. And we bind that port number. So what are some well-known port numbers?
80.
80, which is
HTTP.
HTTP, right? Some other ones,
443,
which is,
HTTPS,
yep,
22.
which is
Secure shell
SSH.
1, 2,
21.
3.
1, 2, 3, which is
NTP.
21.
21,
FTP.
FTP. This is actually 20 and 21.
Yeah.
It's from my presentation.
But you get the idea, right? Is these things are well known and generally not screwed with, right? So in most OSs, in order to bind to those points, it takes administrative access, right? If you want to bind to something, this is 20 and 21, not 20, 21, right? If you have like the ephemeral ports above 1024, then it usually doesn't take administrative access. Right? These are things that you're just gonna do. So the socket, you create a socket, right? This is like an instantiation, then you bind that socket to a port, and then you sit there and listen. Now let's go look at what the other side does. This is UDP, by the way. Just gonna send a packet across the network. So what do we do here?
Create socket.
We create the socket again. Do we bind?
Nope.
No, because we're just gonna have it send, right? Then what do we do?
Send.
Send.
Send, and we're gonna call this send2 because it's UDP. And then, so that actually comes across here, right? In order for something to actually, so listen is a state, but it's not actually ready to do anything yet. What do we gotta call over here to receive that packet?
Accept. Oh, okay. See.
I think it's
RECV.
It's RECV, and this is from, because it's UDP.
Yep.
All right, so we get a receive from, right? Receive from is a blocking call. So it sits there and waits until it gets the packet, right? And then what do we do? If we're gonna send a reply, that's usually how it works, right? Huh? We're gonna do a send to, which means that we need to have a receive from on this side. And then we do that until we're tired of doing it, and then what do?
Close.
Close. So there obviously is not a lot to that, right? Notice that we didn't say that the reply had to be an ACK. It's not necessarily an ACK. A lot of times, for instance, you don't believe that NTP has any ACKs. You request it and you get it. Right? What is some other UDP protocols?
Syslog.
Huh?
Syslog.
Syslog. What else?
DNS.
DNS.
Yeah. Both TCP and UDP.
Yeah. All right. So let's take a look at what's actually happening in here. So inside of the computer, right? We're gonna pass stuff down to the network layer and create a packet. But the computer can have multiple applications running on it, right? Most computers do. So they have multiple applications, right? So each of those applications will create a socket, and when they create that socket, the socket will have a buffer, right? And then that buffer has to pass down to a lower level where all the things are combined together for it to be passed down to the packet, right? So we attach a port number to it, blah, 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 and that happens down here, and where everything is combined, either going down or separated coming up. And then the application, right, can block and ask, and block and ask for things from, and so the buffer is either filled or filled when the application is blocking from the lower layer, or it can be filled when the network is blocking, right? Because there's only so much stuff that you can put in the pipe, right? So there has to be some way to block. But that's really, other than, you know, a lot of big hassle coding this, right? The idea is pretty simple, right? The port becomes a key. That key points to the open socket, and that open socket is either given data or pushes data. That's it. So the UDP, when I said that, is really nothing more than transport basically tacked onto the network layer. The UDP header is literally just the source destination. The length and checksum. Also, the checksum is optional. And if the checksum is zeros all the way, that it's just not included. The checksum includes the checksum for the source and destination address as well. And that is UDP all by itself. So what are some of the downsides to UDP?
It's unreliable.
Scrambled sometimes communication.
Correct. So that things can be out of order. It is unreliable in other ways, right? Things can be lost. What else? So remember, in the network layer, the connection-oriented protocols pick the same path, right? If in a datagram model, it doesn't necessarily pick the same path. And so you could have different costs depending on what was running in between. And so it becomes possible that your UDP packets arrive, they all arrive, but they arrive out of order. What else?
Sometimes they don't arrive at all.
Sometimes they don't arrive at all. Any other things?
If you need to send something big, you gotta break it up and reassemble it yourself.
Yeah, you gotta break it up and reassemble it yourself in the application layer. Which sometimes might not be fun. What else?
If you need to know if it got there, you gotta hack it yourself.
You gotta hack it yourself. And by the way, if you're doing that, If you're breaking them up, then you have to sequence it yourself too, because they can arrive out of order. So, let's talk about how we actually make a connection. So this is super simple, right? Ironically, I think this is the harder out of your project. The UDP's harder. Because what we're going to describe here, TCP just takes care of it for you. It's much more complicated, but it's all just done, right? So, first we want to establish a connection. How do we establish a connection? What do we send to it?
Are you looking for the API calls like you were before, or the
No,
packets?
we'll put in the API calls after we do just the generic communication. Huh? No, we'll do the API calls on the outside first. First, I want to establish a connection, right? So we need something to,
So,
huh? Yeah, or let's just call this connect, right? And then what do we send back?
Yes.
So, something like, sure, connect. So that's their general model, right? Can I connect? Sure. Can I connect from the passive model, right? And then the answer is sure. Why do we do both of those? We could easily accomplish this in two.
you might be able to route from A to B, but not from B to A.
Yeah, right. So there's a number of problems, right? Connect, we want to be able to establish, hey, this is my first datagram,
Mhm.
right? So we're going to establish that first datagram with some kind of number. Let's call this X. So what if the server wants to use a different datagram? Or a sequence number, right?
Yep.
What's the number of its first sequence number? So you get a sure, and then the connect question has its sequence number, Y. So now we both are synced, right? And we don't have to use the same sequence number because there might be reasons we don't want to do that. And then we can verify that we have the correct sequence numbers by incrementing them, right? Every packet we send, we increment, right? So we connected with X, we reply with X plus 1, right? We also ask for connection on Y, and then we reply with Y plus 1. And the reason we do this is it's very robust. If you did it in two, we could come up with ways that things could get really messed up. But if we do it in three, it is extremely robust and very unlikely that even a purposeful attack can mess things up.
That's just for the setup?
Huh?
That's just for the setup?
This is just, hey, we are going to communicate, right?
That's the only time
So,
they have two counters going.
huh?
That's the only time they have two counters going.
No. Every communication after that will have a new counter,
Two
an
counters.
increment.
So you're gonna
So
have a X
every-
counter and a Y counter.
Yeah, every communication that originates with P will have a sequence number of Y plus N, however many it's sent before. And everything that originates with the active will have a sequence number of X plus N. So then we can establish connection, and we got sequence numbers now, which we need to be able to make sure that everything arrives in order, doesn't get dropped, blah, 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 blah. But remember, from the programming model, this TCP is taking all care of this for you, right? This is inside of TCP. So this connect is really a send packet. What does send stand for? Synchronized, right? And then the sure is an ACK, right?
This one should.
Huh?
The second one should be SYNAC.
It is. So technically, these don't have to be sent together. Because this also has a connect and a sure, right? They don't actually have to be sent together. They often are. And then this is an ACK, right? And what is this called overall?
Three-way handshake.
It's the three-way handshake, right? So now, once we get this thing running, sometime we can start sending data. The sequence numbers will be all lined up. We can do some processing inside of TCP to ensure that they all arrive, and we'll talk about two different methods of doing that, arrive in order. But let's take a look at why this is more robust than the three-way handshake is more robust than others. So we're sending packets across the network. So in a very unlikely circumstance, right? Let's say that something goes wrong inside the network, and there is a delay, and then sometimes later you get this packet here arrives at P. And it could be from some past communication. It could be, just imagine that it arrives. It was stuck in the network for some time and arrives. Now, in order for the connection to actually happen, right, we have to have the very second unlike circumstance that ACK arrives also right after it. So two packets got delayed in the network. And then, so ignoring this for right now, in a two-way handshake, right, we could have accidentally established a communication and believe one was actually happening here. It can't happen in a three-way handshake because when we send the acknowledgement, we send our version of Y. Very unlikely that version of Y that's here plus one arrives also.
Well, for the two-way handshake, when a client want to send something, the server has to apply. But if we have two datagrams, two packets arrive to the servers, it's not going to be established with the two-way because the server has to apply.
So let's do it with the same situation with the unlikely circumstance, right?
Okay.
In two-way handshake, what do we get? Connect
Connect.
and sure, right?
Yep.
Which is a sync and an ACK.
Mm-hmm.
This gets it with X,
And this
right?
one's gonna be
And this
one.
is X plus 1. So now, right, let's say this communication happens an hour, really just seconds later, right? You get a connect again that arrives duplicated in an hour, right? And so this third communication would be data. So if this was delayed in the network, now the server would actually believe it has a real connection because the two packets arrived for whatever reason. This could also be malicious.
Go through it one more time, sorry.
So our real communication looks like this. So connect, which we get a synchronized, and this is a two-way handshake, not three. We get an acknowledgement, right? And then the next packet would be data, or actually, it would be data, but it would be the request of the server, right? And then you would get some kind of reply. So imagine that for whatever reason, this arrives and wasn't sent by A, right? And then this arrives in the same situation we talked in the three-way handshake and wasn't sent by A. Maybe it was sent by Jason.
So this is a good way to screw up people's servers
Yes.
in a two-way handshake, so.
But a three-way handshake can't happen because the request back down here is not data, right? This is an ACK. And this is Y plus 1. And Y, the number for Y originated on the server, and the server controls that.
You're saying that the three-way handshake is more robust?
It is way more robust, yes.
It prevents the man in the middle attack, actually?
Now the man in the middle protect is prevented by Diffie Hellman.
So you'd be more like DDoS, right?
Yeah, yeah. But and not that there aren't ways around that, right? But it is extremely robust against accidental attacks, accidental errors in the network, and somewhat robust against malicious. So, after we do this three-way handshake, how do we turn it off? How do we decide that we're going to kill it? So what do we do? Done, right? Finished. And what does the server sense back?
Finish that.
Yeah. And then what do we send down here?
Back.
How do we know that everything actually works out correctly? Right? Because we send sequence numbers here, right?
Mhm.
A sends its own sequence number. The passive P sends its own sequence number, and then A's plus 1, right? And that closes it. So from the perspective of the client over here, the active participant, it's closed the minute it sends out its finish. And then from here, it's closed the minute it receives the finish plus the act, or the act. Not that everything does it nicely, always. So how do you keep at it? Like, let's say the active participant is not nice and doesn't close. How do you do it?
Well, there's a
Just
timer, right?
Yeah, you have timeouts.
We send it again.
Huh?
Oh, this is the CB, so.
So you have a timeout. So, but think and the timeout doesn't have to be all that long, right? Remember, like even if you went and you're like immersed yourself in Facebook, right? and you're on Facebook for an hour. But it doesn't mean that your TCP connection is existing for an hour, right? It's very short bursts. It comes up when you need data and then closes. Comes up when you need data and closes. And so since that cycle is happening inside of the application layer, or inside of your browser from the client perspective, or inside of Facebook from the server perspective, that is inside of the active open loop because your browser's open or because the server application's open. And it just spins and it accepts connections and closes them, right? The timeout doesn't have to be long.
Okay, this one, and then we call it the three-way handshake in normal conditions. But there's another one, it's a four-way handshake for finishing.
So normally, this FIN-ACK looks like this. Looks like that. It's sent in two different packets.
Seems graceful, just both the fin and the act flags on in the same packet.
Huh?
Why don't they just put the fin and the act flags on in the same packet?
They can be done that way, but there are reasons that you might not want to. So if you look at the finite state, the finite automata model, there's two separate conditions, right? You get a FIN-ACK packet or you get a FIN and an ACK packet. All right. Now, we want to send data. In our model, three-way handshake occurs, right? Now we want to send data. Just call these requests and replies. The problem with this model, if we're doing sending data and doing acknowledgement, sending data and doing acknowledgement, sending data and doing acknowledgement, it probably should actually go the other way. But this is the stop and wait protocol. And stop and wait protocol is really, really good on the link layer. Why? Works fine on the link layer. It's short paths, and remember, for a number of reasons, but particularly listening for collision detection, is our packets are the width of the network. Right? So if our packets are the width of the network, and we're doing stop and wait, we're getting 50% efficiency, right? Which isn't great, but it's not bad either. Now, small hop over the internet, right? Our packet is the size of this network. And then it's passed across the network. Now we're much, much lower than 50%. Right? Let's say for argument's sake, these all have the same packet size, right? And there's no switching time or anything, right? What's our efficiency now? Let's make the numbers better. So it's 20% of the original 50%, right? So it's 10%. We're getting 10% efficiency. Does it matter if I have, so this is my home network, right? And right here is my gateway. Does it matter if I have a 10 megabit per second connection or 100 megabit per connection to internet? Do you think it matters in this model?
Nope.
No, it probably doesn't. Unless for some reason your packet size was really big and somehow made it across the network. And the reason is because it's 50%, because by the time we send from this computer to this computer, right, to get the ACK is, what's our formula? It's 2 times the delay, right? So if our delay is D across this network, in order to receive the ACK, we have to traverse it twice. So we get 2 times the distance. And so if, let's now say we're going to do stop and wait, and we have a 1 megabit per second connection, and our delay is 50 milliseconds across the network. This is the internet, right? So 50 milliseconds is not actually unreasonable. So, and our packet size is a standard, what's standard Ethernet packet size?
1500.
1500 bits, right?
Yes.
So we have a 1 megabit per second. It takes 50 milliseconds to traverse the network, and we're going to do stop and wait. What is our effective bandwidth?
One over 2 BD, something like that.
So 2BD is our bandwidth delay product, right? What is that? So our bandwidth is 1 megabit per second, right? So that's 10 to the 6th. So times 5 times, or 50 times 10 to the negative third, right? And then 2 times that. So that is, our bandwidth delay is what?
Raised to the power 4.
Yeah, 100 times 10 to the third is the easiest way to do it. So our bandwidth is 100 times 10 to the third. So how many packets can we stuff in this network and what's our delay? So this is, if we utilize the network perfectly, right? But our delay is 50 milliseconds, so it's 100 millisecond round trip time, right? So if our packets, and we only send 1 packet, one at a time, is stop and wait, right? So it's 1500, and we can do that how many times a second? Milliseconds, right? So we can do that 10 times a second. So we get 15,000 bits. Our effective bandwidth is 15 kilobits per second.
I couldn't see why you were writing the 10. What was the 10 again after 1500 times 10?
Oh, so it's 100 millisecond, I was just jumping
Oh,
through
no,
the math.
no,
There's a 100 millisecond bandwidth delay, right, which means we can send 10, in stop and wait, we can send 10 packets at once, or per second, right, because it takes 100 milliseconds, and then 200, then it takes 10 times, and we get a second, right? So we get 15 kilobits per second is our effective bandwidth. But our actual bandwidth is 1 megabit per second. So we're significantly low, right? And our 15 kilobits over 1 megabit per second is our network utilization in percentage. Whatever that is, it's small. So how do we do this instead?
Sliding.
You do a window. Instead of doing stop and wait, we start firing packets. Let's get them coming back from this way, because this is where they usually come from. And they take some time to traverse across the network. And then, let's say they arrive. And so our communication looks something like this. In this case, our sliding window is a measly 3, but it doesn't really matter what size, right? So we start firing packets. And then when we get them, we start sending acknowledgements. In this way, we can fill our bandwidth up if we pick the right W, which is how many windows we're going to send at one time.
So it's only in stop and wait that the W equals 1, right?
Yes, stop and wait is effectively sliding window where W equals 1. And we've only talked about stop and wait, but up at this point, but in reality, the other layers also use sliding windows. It makes sense, right? The whole point was to utilize the network as much as possible, right? So stop and wait is exactly the sliding window algorithm where the window is 1. So, this is the next question, how do we calculate the number of windows that we need?
It's based on the buffer space?
Huh?
Based on the buffer space?
No, we'll figure out the buffers, yeah, we'll figure out the buffers when we figure out the W. So how do we fill the network?
Don't you start with like a smaller window size and gradually increase it until you start getting negative?
So, yeah, but for this exercise, let's assume that we just know all those numbers already. We know what the bandwidth is, and we know what the delay is. Huh? So we will block when we do the buffers, but we haven't got the buffers yet. We got to figure out how many buffers we need.
Well, once we know the window size, it's basically like if we send, let's say window size is 1,000 and we have sent like 800s.
Mhm.
We know that's left is 200.
Yeah, correct.
So once the 800 that we send has been added and processed, then we can just like open the slots and, that's why it goes, it's a
Yep.
sliding window, we just like slide it.
You're exactly right. We're still jumping. How many windows do we need?
Okay.
How do we figure out how many windows we need?
So what if we do the size of the packets divided by the capacity of the.
Size of the packet divided by the capacity of the network. What's the capacity of the network?
It's how much the passive can take at any point in time.
It's how so the capacity of the network is the bandwidth times the distance, right?
Right.
The distance we usually measure in delay, how long it takes to traverse the network, right? So the capacity of the network is the bandwidth delay product, which we've already discussed. But we also want 2 times the bandwidth delay product, right? And we want that because we want to fill the network all the way up, and so the network has, by the time we miss or get our first acknowledgement, is right after we send out our last packet, our last window.
So would that be 2BD plus 1?
No, it's just 2BD. So 2BD is twice the bandwidth delay bandwidth delay, right? That gives us our capacity of our network, and then how do we work in packet size?
Divide by the packet size, and that's how many packets you send.
Yeah, divide by the packet size, and that's how many packets you send. That's W. So in our case before, somebody's going to need a calculator for this because I'm winging this one. So we have a 1 megabit per second network, right? It's our connection to the internet. And let's assume that it's actually that. And then we had what?
50 millisecond delay.
A 50 millisecond delay and 1500 packet size, right?
Yep.
So in order to fill the network twice, we're going to fill it up twice, because by the time we either get the ACK or miss the ACK, right, we want to have put all of our windows into the network. So that is 2 times what? 10 to the 6th times 50 times 10 to the negative third.
100 times 10 to the third.
Huh?
That was 100 times 10 to the third.
Well, that's good. That's the 2 right here.
Yeah.
And then we divide out the packet size, right? And that's how many packets we can send in this thing. Who did the math? Should we make it easier math? Let's make it easier math. And just divide it. Let's say that we have a 1000-bit packet.
33.3.
For the 1.5.
I have a question. What would you be able to tell them maybe power of -3 from?
Huh?
50 milliseconds.
50 milliseconds. The millisecond, yeah. 10 to the negative 30 seconds. And then we just figure that out, and that becomes the number, that's the number our windows are. How do we figure out what our delay is across the network?
Send the packet and see how long it takes.
Sure. You can figure that out in the connection. It would be a rough guess, right? But or we could take our local area connection and, you know, depend on the network to figure it out. But remember, when we're sending out packets, right, we send them out with the fragment flag turned off, right? So, or the don't fragment flag actually turned on, whatever. And so we can figure out what our size is across the network. That's how we figure out the packet size. And then we figure out the number of windows. Now, so we're gonna send lots of packets, right, before we get acknowledgements.
That equation right there, that was for the number of windows?
This is the number of windows, yeah. So we're gonna send lots of packets before we get an acknowledgement. How do we manage that inside, so before, right, we send out a packet and we get an ACK, right, +1, and we're like, hey, you got the packet, right? And then I send out another packet and you get an ACK, it would now be +3, right? And you're like, hey, you got the packet, right? Right, that was stop and wait. Now I'm gonna send packet. How do we manage that inside of our algorithm? Right, this is where buffers come in. So, start out with the simplest method first. Right, I receive a packet. I stick it inside of my buffer. Let's say we're in the middle of the process. So I stick it here. I receive the first packet, I stick it there, right? I receive the second packet, I stick it there, third, actually should probably go the other way, but let's do it this way first. And we stick them there, right? At some point, we are going to pass that packet up or down, depending on what we're doing, right? And this will go out to the application layer, and we will count it as good, right? Or we send it down and count it as good. Doesn't really matter which direction. How do we keep track of this? So before, we could do it in a single variable, right? Is the acknowledgement one more than the sequence number of the packet I just sent? If it is, then you received it, send the next packet. How do we do it with multiple packets?
Cumulative acknowledgement.
So we are gonna get to cumulative acknowledgement. That's how we will talk about that. Huh? Yeah, but so before we were dealing with just one packet, right? And so it was very sequenced, right? I receive a packet, I send the acknowledgement, and then on this side, you don't send the packet until you receive the acknowledgement. So now we have a problem because you are sending multiple packets, right? Is receiving multiple acknowledgements, right? Which also means that we could do this one of two ways. We can have a timeout value, right, when we receive the acknowledgement for, well, I guess it'd be a much bigger thing. So our timeout lands right between when we think we're going to get the acknowledgement, right? And so when we get this acknowledgement, we shift the timeout down, we shift it down, and we keep one timeout, right? If we do this, we keep one timeout, that means if something goes wrong, we have to flush everything.
Everything or back to where that timeout?
Back to where that timeout, but remember you sent all,
Right.
I mean, we haven't like filled this in, right? So all these are going in, right? And so if we miss an acknowledgement, that means all of these die.
In that window.
And we
for
start
that
back
timeout.
over.
Everything in that window for that timeout dies.
Correct.
I just wanna
Everything
make
in
sure.
that window for the timeout dies.
Yeah, I just wanna make sure.
And in that particular scenario, we don't put anything in the buffer for things that haven't been acknowledged yet, right? So that's not an issue, right? But it would become an issue if we keep multiple timeouts. So imagine we have multiple timeouts. So a sliding timeout value, right? And that way, if we kept multiple timeouts, then it would be possible to catch, like, let's say this one, for whatever reason, didn't make it, right? So this acknowledgement didn't make it, right? But we've sent all these other packets. Then we could actually store these packets down here and ask for this missing packet. But that means that we have to keep multiple timeout values as we slide down. And we have a much more complicated buffer.
So what if we're doing the packet acknowledgement whereby the passive tells the active that this is what I'm expecting based on the packet already received? So like for instance, they all have a number, a sequence number.
Correct.
So the first packet gets delivered, then the passive will send an acknowledgement with the next
Sequence.
packet, sequence number it's expecting.
Mm-hmm.
To prevent having to, well, the only problem with that is if it's a lot of packets, then it's going to cause a lot of delay.
So normally we send with just an incremented sequence.
Right.
One reason that we do that is because incrementing is always fast. And if we're just incrementing, we don't need to keep, at least in that particular counter, we don't need to keep multiple versions of it. So if we just receive a packet and we acknowledge with the sequence number incremented once, it's very fast. What we do have to do is, if we're going to do the multiples, so the first one with the single timeout, by the way, is the most simple, right? Does anybody know what that is called? Is go back in. So if you miss an acknowledgement, you roll back however far you missed, right? So in this particular one, with it was 33 packets, right? We roll back 33 packets and start again. So obviously that gets more and more expensive the larger our bandwidth delay product is. So if our network is very far away or has very high bandwidth, then the cost is significant. So if we keep multiple timeout windows, and we hadn't even talked about this yet, we also have to keep track of what the pointers in this buffer. So in here we have things that have been received and not acknowledgement, and then you have things that have been acknowledged over here, and things that are empty
Process.
here, right, or in process over here. Right, so now we need a pointer for all these. See, with go back in, we only need the front of the queue and the back of the queue. With a where you can pull out an individual sequence and reassemble, then you need pointers, a lot more pointers to keep track of it, right? And so if you're asking for a particular packet, right, so you're selectively asking for that particular packet back, then you need to know where it goes to reorder it. So in go back in, if you receive an out of order acknowledgement, so for whatever reason you get an acknowledgement, either they didn't receive the packet or the acknowledgement was lost in the network, right? That is, you're dead in the water, you start over at the last known good point. If you, in selective repeat, if you receive, don't receive an acknowledgement or you receive an out of order acknowledgement, you go back and ask for that one particular one, right? And fill it back up.
So the second technique is the selective repeat, right?
Selective repeat. And we'll go through that on Wednesday. Maybe we'll actually write an algorithm it. If you hang out just a little bit, I give you your homework back. If you want it, if not, then. With, huh? Yeah, it's right at the very top of my email. I just haven't got to it, but I don't foresee it being an issue.
I just wanted to know if that's what you want.
I don't know.
Because you said
I would
it's
expect
2 pages between 2 to 4 pages.
I don't know.